Okay, it's one fantastic. So we'll continue with 222 now. We're very happy to have Nero tell us something about contact loci of arcs.
Thank you. So there will be some connection, conjectural connection with Floer in this talk. But contact loci, I suppose that for many of you are new things. So I will introduce them in a very basic setup now. You can introduce them at the arc level or the jet level. So let me talk about arcs first in the affine space. And I work over the complex numbers for simplicity in this talk. This is the arc space, the notation for the arc space. And the arc space are what are arcs? Are homomorphisms from algebras. Spec CT to AN. And it's in the setup, because we are working in the alpha space, is the same thing as fixed. So if you fix coordinates, xi, but then it's the same thing as assigning a formal power series to each of the coordinates xi. So those are arcs. And inside here we have the, so we fix f, non-constant polynomial. And we're interested in the singularities of f, of the zero locus of f, typically. So contact loci pertain to the singularities. We take an integer, and we know M contact locus is the space of all arcs, gamma, which have order of contact exactly M with F. So that means when you plug in this power series, formal power series instead of the xi's into F, then you get a non-zero coefficient T to it dm plus higher order terms in T. You can already see that this is the arc space is an infinite dimensional affine space. So when you assign a formal power series, you have coefficients xi j for every power j. And the xij's are the coordinates of the arc space, of the affine space. But in fact, you can understand everything at a finite level. So let's, M is fixed. We can look at M jets. And the M jets are defined similarly, except we truncate on level M. So instead of assigning formal power series, you assign formal power series modulo T to the M plus 1. So then this becomes more manageable. Times n plus 1 coordinates. So it's an affine space. And inside here, we can also define, so every time I use the arc version of the M contact locus, I'm going to put an infinity there. If I don't put an infinity, it's the jet level of the contact locus, so it's defined similarly. We look at the M jets, where this thing happens, modulo T to the M plus 1. So it's the same definition. Now, the truncation map will give you a map from the arc space to the M jet space, and this is a it's a trivial fibration over this affine space with fibers, infinite dimensional affine space given by the coordinates that you don't see here. And moreover, this is just the pullback under this truncation map. of the M contact locus here. It is clear that these M contact loci are locally closed subschemes. And I'll show you how to get the equations for this immediately. And if you understand everything about them at this finite dimension level, then because this is a trivial vibration, affine spaces as fibers, then you understand everything about it. So I will alternate between these 2 points of view. They're pretty much equivalent, but some arguments you might need to pass to arcs to make the arguments work, and I'll point out where. So this is the M contact locus of F. So as I said, you have every time you have a polynomial, you have very explicit equations here. So let me tell you how you do that. That's one of the advantages of working with contact loci. Everything is explicit. So let me take, for example, the cusp. That's with the Grothendieck. So an arc now is replacing X with a formal power series, T. And Y, the formal power series of T. And if you want to compute the M contact locus, you have to plug in those power series into F and look at the coefficients of powers of T. So let me call those F0, F1, F2, and so on. X0 is X, Y0 is Y, and here's an F0 becomes F, and here's how you get the other coefficients. So there's an easy trick. Define a formal derivation that sends the xi to xi plus 1 and yi to yi plus 1. And with derivation, with this formal derivation, derivate f. So you get f1 2y y1 minus 3x squared x1 f2 y1 squared y2 minus 3 and so on 2x x1 squared plus x squared x2 and so on. And then if you want, for example, the third contact locus of F, then this is given by the zero locus of, well, I need order exactly 3, so all the coefficients of powers of t are 0 up to power 2 inclusive. And then I have to remove the zero locus of F3, which I can get by further derivative. So this is very explicit. I might have been lying a little bit here. You might have to put the factorials here to make it look like Taylor series, but this last line is not a line, it's the same. So they have the advantage of being very explicit, the contact loci. The disadvantage is that we know very little about it. And in fact, this talk is about some of the most basic questions about the topology. We consider the following questions. What are the reducible components? And how do you compute cohomology of this? So let me just mention now that this can be defined in a more general setup. And the general setup that we aim for is the following. So we can define the M contact locus of arcs in a smooth complex algebraic variety. So that will replace the affine space, where the role of F is replaced by a divisor, effective divisor, hypersurface. And sometimes it's also useful to focus, to concentrate what you're looking at. For example, you might want just arcs that are centered at the singularity. There's always a center by making t equals 0 on both sides. That gives you the center. So you fix a subset, a closed subset of D in the support of D, which plays the role of centers of your arcs. So then you can define this contact loci. A slight variation of this is the following. You can impose an extra condition. You impose that this coefficient here is exactly 1. So that gives you a subset of this contact loci. So if you impose in addition that this is 1, then, excuse me for this, but I will use the following notation, which is not very... I put a bar, and we call this the restricted contact loci. Restricted M contact locus. They have the additional feature that they come with an action of the group of M roots of unity on them. In fact, they remember a bit more about their singularities. Why are we interested in this? What's the motivation for looking at this? Is the following. So, if you make a generating series for the classes and appropriate Grothendieck groups of this contact loci, so slightly normalized, and here is dimension of x. So these are the classes in the Grothendieck group of complex varieties. This is the so-called motivic zeta function. Let's say we're in the polynomial case of f. In fact, this is the so-called naive motivic zeta function. The real motivic zeta function is the one for restricted contact loci, which also, you take the classes in a Grothendieck group of varieties that come with an action of roots of unity on them. So that's the motivic zeta function of Denef and Leuven. And Denef and Leuven showed that this is a rational function in a certain sense in T. So therefore, there's a notion of poles. There are finitely many of those poles. Those are rational numbers. And the conjecture of Gusa, done in the Piatti case and then rephrased by Denef and Leuven in terms of these motivic things, states, the monodromy conjecture states that these rational numbers, if you take e to the 2 pi I of them, you get the roots of the monodromy, of the eigenvalues of the monodromy, acting on the cohomology of the Milnor fibers of the polynomial. This conjecture is widely open. It's one of the most mysterious things in singularity theory.
What is this L?
Yeah, sorry. L is the class of A1. In Grothendieck group of varieties of the complex numbers. So, no one really understands these poles. So we're trying to understand the contact loci or restricted contact loci.
Could you say again what the effective divisor was before? I missed that.
It's a generalization of the fact that we're considering a polynomial.
So you get a tangency of order n?
You can define, so you replace an by x, so you have the R alpha in n space, and then, yeah, okay, so then you have to, yeah, so then you can define the order of D of gamma along D. So gamma will have a center on D, and the order of tangency there has to be exactly. And you're asking that center lies in this subset of D. For example, sigma could be the singular locus of D. That's the more general setup. Well, not the most general, we can also envision making x singular. But for this talk, we'll keep x smooth.
If you multiply f with a non-zero constant, then your right-hand side changes by that non-zero constant.
Yes.
And then your star thing is no longer 1.
Yes.
So that's a bit weird. If you want to glue things from different patches of the divisor with different f's, and then
Yes. So the restricted one, let me just consider in the case when you have a regular function instead of the divisor. So the non-restricted one the non-restricted version is available in this bigger set.
This conjecture is about just an.
This you can make it just for a polynomial. Yeah. And it's still, we still don't, there's no program to solve this. There's no conceptual explanation. There are a handful of cases of classes of singularities where the monodromy conjecture is known, but there is no there is no idea how to do this. So that's why we're looking at this. Now, we know quite a lot of the piecewise geometry of the contact or restricted contact loci. One of those is the fact that this is a rational function. In some sense, this means that in the these classes in the Grothendieck group, you only need to know the first few ones and then you know the rest. That's some information from the piecewise geometry of this. But the questions that are addressed today, they deal with the global geometry, with the global topology. So let me state an ideal outcome, which almost never happens besides in the following case.
Can you maybe give us of this zeta function, which you know everything about?
So let me make a topological realization of it. Which is almost taking the Euler characteristic, but not quite yet. You have to do something before. You have to get rid of L minus 1, because that's C star, and if you take Euler characteristic of that, you make everything 0. So anyway, you get the topological zeta function from the motivic one, and I'll do it for the cusp. Well, I can tell you what's on the bottom. S plus 1. So S will be I need to specialize here the T. Well, things specialize. So I have one variable here that from capital T I end up with this one. So let me just tell you exactly what the poles are. So -1, -5/6, and -7/6, and there's something here. The reason why you can compute this very easily, if you have a log resolution of your polynomial, then there is a formula of Denef and Leuven that expresses this in terms of the log resolution as a finite sum of rational functions. And in fact, it's that formula that proves that this is a rational function. And then you can specialize that with all the characteristics or to the Grothendieck group of mixed force structures, and you can get, instead of working with these classes, you can work with something more concrete. So the bottom line is that the poles here are the negatives of these numbers. So e to the 2 pi I of -1, -5/6, and -7/6 are supposed to be monodromy eigenvalues, which they are.
You say you get this thing for that example on the left?
Yes. For this one. This is for the cusp. Okay. Let me say something for a particular class of examples, so this is like the ideal theorem, but it will never hold in general. This is for hyperplane arrangements. So product of linear polynomials. So the restricted contact locus, we can write this down explicitly as complements.
Rotations are restricted.
This one is, here I'll tell you what the difference is between restricted and non-restricted, so you have a feeling about these two. The first one is non-restricted. This is a finite disjoint union of complements of associated hyperplane arrangements, subarrangements. And because everything is explicit, then you can compute their cohomology. And so this is expressed as the cohomology. These are cohomology rings of complements of hyperplane arrangements. And there's a theorem of Orlik and Solomon saying that this is a combinatorial, explicit combinatorial invariant. So you have an explicit combinatorial formula for this ring. So you're very happy in this case. Now, if you look at the restricted case, these are the same finite unions, but now not of the complements, but of the Milnor fibers.
So what's associated hyperplane?
Yeah, so you start with the original arrangement, and the combinatorics of this arrangement associates you other arrangements. For example, you have a hyperplane there, and then you have all the other hyperplanes meeting this, and you have an induced arrangement, subarrangement in that hyperplane.
Is it just a Bergman thing, or I mean, what's the combinatorics is in the Bergman thing,
It's
roughly speaking.
yeah, but it's not so. I don't think we found a formula. It always differs. Yeah, for every n there's something else. So I cannot say it's the Bergman factor. That's only one thing. So you have to take that into account. But there's a very explicit way of writing it. Now,
I'm not sure I understand the statement. So you start with one hyperplane arrangement, and then you have to take some associated.
for every n, there is a combinatorial procedure to write this as a disjoint, topological disjoint union of complements of hyperplane arrangement that you associate combinatorially from those.
But those are like,
Yeah?
so those are different from the original one. For every n, you would have a
Different, but also the original one can appear up to multiplying with some affine spaces. Yeah. And the restricted contact loci are the same disjoint unions out of the Milnor fiber. So let's make now the assumption that we're looking at arrangements of linear forms. So they all pass through the origin. And now I'm looking at the arcs in the contact loci only centered at the origin. So then I can make the statement that there is a Milnor fiber at the origin. The disjoint union of Milnor fibers of these things. Now, there's an old Folklore conjecture that the Bethe numbers of the Milnor fibers of hyperplane arrangements are combinatorial invariants, but there's not even a formula for that yet. So we cannot conclude the same thing, but that's up to do. The ball is kicked into the field of hyperplane arrangements right now, so to speak. So this is a bit more subtle than this. Just like the Milnor fiber of a homogeneous polynomial is more subtle than the complement in the projective plane of the zero locus of that. Okay. So before I state our results, I need to summarize in 1-2 lines the source of all our knowledge about the piecewise geometry of the contact loci. And it's phrased in terms of the following. So I'm going to be in this more general setup here. X is a smooth variety, and D is a divisor, and we take a log resolution of D and of sigma. So we blow up everything until it becomes simple number crossings. Let me call this mu. And we can write the pullback of the divisor as another divisor with some coefficients, ni. The index set is, let's say, S for this divisor. So this EI is a simple number crossing. I also need a notation for the coefficients of the relative canonical divisor. And I'll call them nu I minus 1. And an extra assumption to make things easier for us, which we can always achieve, is that this resolution is M separating. And M separating means the following. Every time two different irreducible components of the pullback of your divisor upstairs intersect, then the sum of their multiplicities have to be greater than M. If you start with a log resolution, you can always keep blowing up further intersection loci until you achieve the M separating condition. And with this condition, we have the following. We can write the contact loci, or even the restricted one. There's not big of a difference. I'll tell you what the difference is. But I better do this first at the arc level. As a disjoint union, but not topological. So it's a partition. In terms of parts, I'm going to note it like this. This is for I, such that Ni divides M, and we also want that this EI contract to where we want the centers of our arcs to be. And we call this SM, is a subset of S. Now, what are these? These are, so we are somewhere, we've blown up our singularity, and every arc here, and that's why we work with arcs now, that has a positive contact order, its main body lives outside the divisor. So by the valuative criteria of properness, it lives uniquely to an arc on the resolution. And because it has a certain order of contact, a positive order of contact with the divisor, it has to have center somewhere on the inverse image of the divisor. And because it is M separating, it cannot have a center in an intersection. So it will lift uniquely to an arc that intersects exactly one of the divisors out there. And the order of contact with F has to be, with the divisor has to be M, so that's why we get Ni has to divide F. So this is the set of arcs in the M contact locus such that the center of the unique lift belongs to EI naught. And EI naught is EI without the rest. We know everything about this. These are smooth one empty. We know the correlations. We know that there are homotopy equivalent in a very explicit way to, well, almost to EI naught, but there is also a canonical cyclic coverage of degree Ni that one has to take in this business. And here, let me tell you what the difference is with the non-restricted contact loci. We have the same decomposition, and again, we know everything about these species, but those are homotopy equivalent with a circle normal bundle to EI naught instead of with this finite cyclic cover.
Maybe it's convenient to say that this EI dot tilde is the piece of the Milnor fiber that lives close to EI.
Yes. So our composite model deals exactly with this strata EI for the monodromy.
So if this restriction embraces the contact loci also could be restricted, right? The X
Yes. Okay. So this is good enough to do piecewise geometry in Grothendieck group of varieties, but it's not good enough to tell you irreducible components or anything about the global geometry because, as one of our students discovered, this is not even a stratification. So it's just a partition. So we don't even have a stratification at the moment. This is just a partition. We don't know what happens with the closure of this thing. That's the big mistake. So the first theorem that we addressed was how to compute the cohomology of contact loci. This is the Javi. Lucky Twang and Hongduk here. And it says the following. We fix W a relative ample divisor. And then with this W, we concoct a spectral sequence, cohomological spectral sequence. With the first E1 page being very explicit in terms of the resolution. So we have the homology of this cyclic covariance, which converges to the cohomology with compact supports of the M contact locus, restricted M contact locus of F, where in the case of a polynomial F. And we can put condition on sigma, if we want. Okay, so it looks technical, but what we wanted actually, we wanted to get this theorem by reverse engineering because the idea for this came from a paper by McLean, who constructed a spectral sequence with the same E1 page, converging to the Floer cohomology of the fixed point Floer cohomology of the M theta rate, and there's a condition there, of the Milnor monodromy. So this is the monodromy. If of F, if F has an isolated singularity. So it's the Milnor monodromy of this hypersurface singularity germ. So a course, the differentials, we don't know how to make them agree. In fact, that's our conjecture, that these two things should agree. So the conjecture is that up to some shift in the total degree, the cohomology with compact support of the M contact locus of isolated hypersurface singularity, if you fix yourself with the ox at the origin, is the same as the Floer fixed Floer cohomology of the empty iterated monoid. So there's another conjecture this week on these things. Okay. The status of this conjecture is the following. So this is okay for M being the multiplicity. And our two students, Javier de la Bodega and Eduardo de Lorenzo Poza, have proved it for plane curves.
Well, the three-dimensional part is also okay for M smaller than multiplicity where both sides vanish.
That is all, okay, yeah, sure. But yeah, both sides vanish for M smaller than multiplicity. Their proof, unfortunately, as I mean, the whole point of this would be that you have something algebraic completed something symplectic. Their proof is by completing both sides and seeing that they agree. This is just as vector space dimensions, so no product yet.
It's a very interesting remark that the M in is, I mean, it's very close to what I was talking about, right? The xm was a 1 over d to the points. So I would have xd, I look at these order kind of arcs. I looked at the disk, right? But you can look at the corresponding arc at the center fiber.
Yeah.
And that would give an element of this x over.
Yeah, so one could.
Right, so they're labeled by 1 over d into the points. The connected components of the x in this case, I think. For these degenerations of Calabi-Yau that I looked at.
We cannot say, so we have a very tough time saying something about the connected points. You will see what the statement is for plane curves. That's by no means an easy thing for us. So this, again, this is not a topological disjointing. This is just a partition of a set.
Same thing, I guess.
No, you need to understand the closures of this thing to say anything about connected components. So it's will answer to some extent.
I'm not making any statement about the Euclidean. No, I'm just saying the labeling set would be the same.
Ah, the labeling.
And we would associate these generators of the mirror ring are labeled by these things. So we have one generator for each 1 over d integral points, like contact points on the central fiber. That would be your center together with the with the contact order.
I see. Yeah, so, but your context is a bit different. You can do a monodromy at infinity in some sense in a global situation.
Not so fundamentally different. I don't think so, but we can talk about it. Yeah.
So you're missing an F to declare an order.
No, we have an F.
But
the F is this projection. F equals 0 would be the central fiber. That's the D.
So you have an F equal 0 in your setting.
Yeah.
Yes, you have
It's
a map.
x0.
But we
Just
have
defined a map in your like log PSS map is a map between these
we
two
are
groups, right?
if you take a log
Yeah.
if you take a log resolution, you get another G.
Ours is already log resolved. It's not one of those things.
And if you have one single that's good. Then yeah, there is a big difference between the M contact locus of the pullback function here and this. In fact, that's the
No,
That's how you get this from that contact locus, but you cannot.
yeah, we
say
don't have
anything.
to. I mean, everything is resolved from the beginning. Right? It's a kind of trigger case.
Yeah, but then the conjecture will not be true for that setting. So here what is very important is that F is not resolved. So it's the minimal possible moment of this smooth.
Yeah, we start with something that's like this, and here you could.
I'm confused. If
Yeah, but the monodromy is the same.
Yeah,
It's
exactly.
resolved.
Monogamy is the same, but the
But
contact
contact loci
are not.
So what are you assuming then? Do you assume it isolates in there?
So if you assume simple normal crossings, you know everything about the contact loci.
Yes.
Everything. But if you don't, you don't. This is much more difficult.
Right.
I just showed you what
I
the
see.
equations for this are. Try to say without.
So you're making a stronger statement. That's what you want to say. You're making a statement downstairs about the contact
Yes.
class downstairs. I see. Yeah, I don't care. Sorry.
Yeah,
Well,
yeah, but
one interesting thing is that this doesn't involve any mirror thing to say. Well,
No,
We don't know how
mine
true
doesn't
this
either.
is.
Mine doesn't either. No, this is not a
direct. He just defined a map from the right hand side to the left hand
Yeah,
side. I feel
No, it's the
this
same.
cannot be. It must be the same thing.
I think so.
okay. Let me just say also that the conjecture is compatible with the result and all the results after taking all the characteristics on both sides. So if you take all the characteristics, then you would recover an older theorem of the Leuven and later reproved by Bushowski and Leuven, namely that the Euler characteristic of the contact locus is the nth Lefschetz number of the monodromy. I have to put the Miller fiber of F here. That's the Miller fiber of F. So that is well known to be one characteristic there. In fact, in the original paper of the Leuven on motivic zeta functions, where these contact loci appear, and they noted that this happens, they had the following remark: that Paul Seidel, when he saw this equality, he said, "But this is something that we can get from fixed point Floer cohomology." So they attributed to Seidel the question: what's the relation between the contact loci and this? And MacLean reiterated that question when he came up with his spectral sequence, that there might be a connection. So our conjecture tries to answer that question in a very precise way. So the next topic deals with finding the irreducible components, and that's also known as the embedded Nash problem. And a different way of stating is to determine geometrically the irreducible components of the contact loci, restricted or not. And we know from this decomposition here that every irreducible component is the closure of something like this. So there are some of these EIs that are more special than the others, because they give irreducible components. The question is which ones. So equivalently, which EI give the closure of this stratum as an irreducible component of the end contact locus. And these are non-empty, smooth, irreducible.
I think I'm missing something fundamental. So why is, if each arc lives uniquely to your resolution, why is the XM so much more complicated than the XM upstairs?
Because
Because of Floer differential.
Well, essentially,
Yeah, but I think it kicks in at the first E1 page.
I'm talking about the spaces, not about homology.
So you get a bijection between two sets, yeah, but it's not bicontinuous.
and the point, so from the point that the arc that leads to one component might very well deform to something
I see.
far away.
It's just a bijection. And in fact, studying pieces on which you can make sense of this bijection, in terms of vibration and so on, that you understand, is exactly the content of this statement.
And the content of last type problems is to understand when you can approximate all the arcs that appear in one device or by arcs that appear in one.
Or understand all closures of these pieces. Okay, so the next is a partial answer to this embedded. By the way, the embedded mesh problem was posed by Ian Lazarsfeld and Mustatse in 2004. It's an analog of the classical mesh problem. It's an embedded analog of the classical mesh problem. So this is also joint work with Harvey. The two students and Thomas. So we are in the setup as before. X is smooth, and D now has to be reduced. This is something we did not impose before. And the sigma anything closed in there in this form. Suppose again we take an M separating log resolution. Everything will go through that notion. We fix M. Take an M separating log resolution as before. We have these EIs. Suppose EI is not contracted. Actually, I don't have to take an M separating log resolution. Take any log resolution. Suppose EI is not contracted. On a minimal model of Y, and I have to write a pair for a log minimal model here, and the pair is going to be the inverse image of D reduced plus the divisor. And we do a relative minimal model over X. So the minimal model program gives you some modifications. You keep contracting things and flipping until you get something supposedly better with respect to the relative canonical divisor or the low canonical divisor. And as a result of that, you might have contracted some of these components here. But suppose EI is one of those that is not contracted for some resolution. In principle, for a particular resolution, you'll have many models, but the same divisors get contracted or not. But if you do other resolutions, other divisors might get contracted. So suppose EI is not contracted for one minimal model of one log resolution. And then we have one of these mesh components. So this is an irreducible component of the M contact locus for all M divisible by Ni. as far as the embedded Nash problem is concerned, this is just a partial answer. On the other hand, as far as the minimal model program is concerned, there's a full explanation of divisors that do not get contracted with minimal models, which it's a different explanation than what they had before. This is this is an embedded analog of the Nash problem. The Nash problem deals with singular varieties without having them embedded anywhere. And the Nash problem asks about the irreducible components of the subset of arcs that passes through the singularity. That was solved by Hardy and Maia for surfaces. And in higher dimensions, the best result is a partial result by Defernay and Docampo, who showed that if you take a resolution and then you take a minimal model, relative minimal model, then the components that do not contract from the exception locus will give you irreducible components in the Nash sense. That particular state, so it looks similar to this. So this is a complete analog of that, but the proofs are different. However, in the absolute Nash case, the partial result of Defernay and Docampo applied to the dimension 2 case gives you the full answer to the Nash problem because of the existence of minimal resolutions for surfaces. This is not the case here. So one has to do extra work to prove, to fully give an answer to the embedded Nash problem for plane curved gems. This was done.
Is this minimal model in which sense?
In Mori
More
sense.
sense.
Yeah. So you look at ky plus the reduced locus of the pullback and you intersect it with curves in the fibers. And whenever you find something that's negative, you contract those Russian curves. And in the end, you get something, y prime delta prime, that's relative nef. Yeah. So we do have a full answer in. So we have a combinatorial solution to the embedded Nash problem. And dimension 2, so for plane curve germs, this is x, d, and sigma. We, in our paper, was for unibranch germs. However, the two students did it in general. So without the unibranch case, that's Javi de la Bodega and Eduardo. And let me tell you what this solution is in an example. In fact, in general first, and then in the example for the task. I should not have erased this. So we have, every time you have a plane curve germ, then you take the minimal resolution, log resolution, and you form the dual graph of that. So the dual graph for a let me do the unibranch case, it looks something like this. This is the state transform. Something like that. That's the dual graph of the minimal resolution. So you decorate this with the NIs, the orders of vanishing. And we're looking at the M contact locus. We want to figure out the M contact locus, the irreducible components. We have the decomposition into parts with Ni dividing M, and we're looking just at the origin, so we never care about this component here. So just the exceptional vertices. However, the algorithm must do the following. So starting from this, you compute the minimal M separating log resolution. So M separating means, I'll remind you, every time you have two intersections, these multiplicities have to add up to something bigger than M. So you keep blowing up if necessary. You might have to blow up here too. But it's a combinatorial process which determines fully the minimal M separating dual graph. So now we have that. We only look at those divisors with ni dividing n. So they might be here, 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 here. Now, the irreducible components, so every time you have a divisor with ni dividing m on the horizontal bar, it will give you an irreducible component. That's one fact. And those on the horizontal bar are exactly the ones given by the minimal model approach. However, there are also the ones on the vertical things. Every vertical thing that contains one of those divisors with an I dividing m will also give you one irreducible component, and the dominating, the part that eats up all of them is the one that's the closest to the rupture point. It could be the rupture point itself, in which case there's only one component. So that's the algorithm, and moreover, these irreducible components also give you the connected component decomposition. It's a special case for plane curves. So let me illustrate it for the cusp.
Can you say this again? So the ones on the kind of connecting one to the C total, they are always components.
Everyone from you will give you a irreducible equivalently connected component.
And then the ones downstairs, only the ones like these.
There could be new components. For example, this one did not appear from anything from there.
But it's one component.
It's one component, only one component. And it's dominated by the vertex closest to the rupture component with ni dividing m. It could be the rupture component itself, in which case you already knew that you had the component. But now you also know that these guys sit in the closure of that.
Can you have legs without any?
You could have legs without anything. One thing, in this part, you can, if there are vertices with ni dividing m on this vertical thing, they can only occur either here or on one of the two sides, but not on both. So the notion of the closest to the rupture component still makes sense. And the algorithm that I mentioned applies. So let me illustrate this for the cusp. And the goal will be to find the 8 contact locus. So here we have, this is C tilde, we have E1, E2, and E3. And the multiplicities Ni are like this: 2, 1 here for C, 3 for E2, and 6 for E3. So the dual graph of the minimal log resolution is the following. This is E1, E2, E3, and C tilde. So we have the multiplicities 2, 3, 6, and 1 here. We want an 8 separating log resolution. So this is not an 8 separating log resolution because 6 plus 1 is smaller than 8. So we have to blow up the intersection point here. Into this E4 with multiplicity 7. 7 plus 1 again, we need to blow up that intersection one more time. So now we have, this satisfies the 8 separating condition here. 8 separating condition is satisfied here, but not here. 6 plus 2 is exactly 8. We need to make that bigger, so we blow up one more time. And this is now, this is the minimal 8 separating log resolution. Of the cusp. So now we're looking at those exceptional vertices with multiplicity dividing 8. this one, and this one. So we have the 8 contact locus. We know that this is given by the arcs that lift uniquely to E1, the arcs that lift uniquely to E6, here, and this one, the arcs that lift uniquely to E8. But the algorithm tells you that this is one irreducible component, and that this is one irreducible component, and it is dominated by this guy here. And they're both, and they are disjoint components as well. And that's the algorithm for, at least for unibranch case. For sorry. Sorry.
Yeah, it's not.
One of them is E5. E6 is interesting.
E5, sorry.
5,
This is E5. That's this guy here.
and there should be E6 and
E6 and E1. Yeah. So
there is no E8.
this is only one guy, and then we have the other two. Oh, yeah. Yeah, sorry. That's all. I think that's